In the 1950s, commercial aviation expanded faster than the infrastructure supporting it. As passenger volume surged, the manual systems used to track who was sitting on which plane completely collapsed under the load. Tracking inventory meant relying on localized, physical records. Clerks wrote passenger names on color-coded index cards and updated flight seat counts using massive, wall-sized magnetic boards. If a customer walked up to a counter in Miami to book a flight out of Chicago, the agent couldn't just look up a screen. They had to initiate a long chain of teletype messages and long-distance phone calls to physically verify an open seat. In computer science, state management refers to tracking the exact status of a system at a specific moment in time. In this era, state management was entirely physical. The authoritative data for a flight lived exclusively on a chalkboard or cardboard in a specific room. Because these records were scattered across different cities and individual airport offices, there was no centralized mechanism to view the entire airline's available inventory simultaneously. A physical, disconnected system relies on asynchronous updates, meaning data is processed much later, not instantly. This structural delay created a strict limit on how many passengers the industry could effectively handle. When data states are updated asynchronously across vast geographic distances, information inevitably falls out of sync. This delay introduced a major structural flaw known as a concurrency failure. A concurrency failure happens when multiple users attempt to read and modify the exact same piece of data at the exact same time, leading to overlapping claims. Look at this conceptual model of an inventory card for a flight. An agent in Boston and an agent in Dallas might call into the central hub at roughly the same time. Because the physical seat card hasn't been updated yet, both agents are told that seat 4A is empty. Both remote offices process the sale. Their separate approvals collide on the same physical record, entirely corrupting the inventory data. On the ground, this meant flights routinely oversold. Airlines lost revenue issuing refunds, and gate agents spent hours manually resolving disputes as passengers arrived to find their assigned seats already taken. Until a network could lock a piece of data and guarantee strict consistency across every geographic location at the exact same millisecond, real-time commercial operations were scientifically impossible. In 1953, American Airlines president C.R. Smith boarded a flight and happened to sit next to a senior sales executive named Blair Smith. They represented two massive organizations with perfectly complementary problems. American Airlines needed a way to track its seating inventory synchronously. Blair Smith worked for IBM, which needed a commercial challenge complex enough to prove that enterprise computing was viable outside of military applications. Their conversation led to a joint engineering venture they called the Semi-Automated Business Research Environment, or SABRE. The commitment required massive capital. American Airlines invested $40 million, comparable to hundreds of millions today, into the research and development of the system. The engineering mandate was absolute: eradicate the manual index cards completely and establish a single, globally accessible digital state that updated synchronously. They had to construct this architecture from scratch. There were no relational databases, no structured query language, and no established network protocols for remote data transmission. SABRE became the ultimate test environment. The solutions IBM engineered to track airline seats would directly dictate how future high-stakes digital transactions would be processed. The first technical hurdle was data retrieval. Early computers relied on sequential magnetic tape. If you needed a specific passenger record, the machine had to physically spool through miles of tape to find it, a process entirely too slow for a live booking environment. IBM had to pivot its hardware strategy to overcome this massive physical bottleneck. They bypassed linear tape by utilizing magnetic drum memory alongside their earliest iterations of disk drives. This architecture allowed for random access memory. Instead of reading sequentially, the system's read and write heads could instantly jump to any specific sector on the spinning drum, retrieving inventory data in fractions of a second. The required throughput was immense. This hardware needed to support over 1,000 reservation agents querying and modifying the central database simultaneously. To process this concurrency load, IBM deployed the 7090 mainframe. It was a massive, fully transistorized machine, capable of executing over 200,000 instructions per second. Keeping these systems running required an intense operational footprint. Engineers continually monitored the mainframe consoles. balancing the processing loads and manually managing the peripheral storage units to prevent hardware crashes. By abandoning linear tape and shifting entirely to random access magnetic drums, IBM created the specific storage architecture required to execute parallel data processing at an industrial scale. Centralizing all data into a single location introduced a catastrophic risk. If the mainframe went down, the entire airline's operation would halt. In computing, designing a system to avoid this single point of failure is called ensuring high availability. SABRE solved this physical risk through strict redundancy. Two identical IBM 790 mainframes process the incoming transaction streams simultaneously. If the primary unit suffered a hardware fault, a failover protocol automatically routed all traffic to the secondary mainframe, absorbing the load instantly without dropping data. With the central database secured, engineers had to build a network capable of connecting remote ticket agents directly to the processing core. They achieved this using teleprocessing. By leasing thousands of miles of dedicated telephone lines, they bypassed the latency of public communication networks entirely. This network connected 1,500 terminals across the country to the central mainframe in New York. When a Los Angeles agent confirmed a ticket, a direct pulse instantly modified the central database, which then immediately blocked simultaneous booking attempts, ending concurrency failures. By centralizing data state and decentralizing terminal access, this massive teleprocessing network became the earliest functional model of what we now call cloud computing. The deployment gave American Airlines immediate dominance in the market. SABRE eradicated double bookings and reduced the time it took to confirm a seat from several hours down to 3 seconds. While the physical transistors and magnetic drums of the 790 mainframe eventually aged out, the software logic governing these massive data interactions proved incredibly resilient. This block represents the underlying control logic that originally powered SABRE. The processing efficiency was so high that IBM extracted the raw transaction logic, stripped out airline-specific variables, and released it as the Airline Control Program. As other industries adopted it, the codebase evolved once more, becoming the Transaction Processing Facility, or TPF. TPF is an operating system explicitly built for raw speed and scale. Today, it still actively manages the world's most critical data, handling major credit card networks, clearing financial exchange trades, and routing global aviation databases. With almost zero system overhead, it remains the most mathematically efficient way to process extreme volumes of concurrent data without dropping a single packet. Decades before relational databases, long before the internet, and well before the concept of cloud computing even had a name, the engineers behind SABRE mapped the precise architecture of real-time digital logic. That blueprint still runs the modern global economy.